Everything you did today was powered by one equation. You unlocked your phone and it was there. You connected to Wi-Fi and it was there. You streamed a song, loaded an image, sent a text, scrolled through a feed, and every single one of those actions was processed by the same piece of mathematics. If you have ever had an MRI, that equation looked inside your body. If you have ever made a phone call over 4G or 5G, that equation carried your voice. If you have ever used noise-cancelling headphones, that equation is the reason they work. And the man who wrote it was not a mathematician. He was an orphan, the 9th of 12 children, born to a tailor in Burgundy in 1768. His mother died when he was 9. His father died the following year. He was raised by monks in a military school where he was denied a commission in the engineering corps because he was not born noble. He nearly had his head removed by the guillotine. Twice, he survived the French Revolution by accident, accompanied Napoleon to Egypt, governed a province in the Alps, and spent the last years of his life wrapped in blankets in an overheated apartment in Paris because he could not get warm. He was obsessed with heat, not metaphorically, physically. He kept his room so hot that visitors could barely breathe. And the equation he wrote was about heat. It was about how warmth moves through a metal bar. That is it. That is what it was designed for. How heat spreads through solid objects. Not music, not images, not telecommunications, not medicine, not the detection of gravitational waves from colliding black holes a billion light years away. A metal bar getting warm. And yet that equation, written by a man with no formal training in pure mathematics, rejected by the greatest mathematicians of his era, suppressed for 15 years before it was allowed to be published, now runs the infrastructure of human civilization. Not as a metaphor, literally. Your phone is computing it right now as you listen to this, thousands of times per second. Every Wi-Fi router on the planet is computing it continuously. Every cell tower, every MRI machine, every digital camera, every streaming service, every voice assistant, every satellite. The conservative estimate of economic activity that depends on this single equation exceeds $2 trillion annually. And the man who wrote it was told to his face by the most respected mathematician alive that his central claim was absurd. His name was Joseph Fourier, and I need you to understand something about his story before we go any further. This is not a story about a clever math trick that turned out to be useful. That is the version you were taught, if you were taught anything about it at all. The real version is different, and it is deeply strange, because the equation Fourier wrote does not just work on heat. It does not just work on sound. It does not just work on images and radio waves and medical scans. It works on the fundamental structure of physical reality itself. The Heisenberg uncertainty principle, the thing you were told is a deep mystery of quantum mechanics, is actually a mathematical property of Fourier's equation. It was true before quantum mechanics existed. It would be true in a universe with entirely different physics. Particles, the electrons and photons and quarks that make up everything you can see and touch and feel are not objects that happen to be describable by Fourier's mathematics. In quantum field theory, particles are excitations of Fourier modes. They are vibrations, not like vibrations, not analogous to vibrations. They are vibrations, and the equation that describes them was written by an orphaned tailor's son who was trying to figure out why one end of a metal bar gets warm before the other. That sentence is going to take on a meaning that I do not think Fourier intended, and it is going to haunt the rest of the story. Because what I am about to show you is not just the history of an equation, it is an investigation into a question that nobody has adequately answered. Why does an equation designed for heat conduction in 1807 turn out to be the operating language of reality itself? Why does the universe decompose into sine waves? Why do smooth, rolling, periodic curves appear to be the fundamental vocabulary in which physical law is written? And what does it mean that a political prisoner and colonial administrator, a man the mathematical establishment treated as an amateur, stumbled onto this by accident while trying to solve what amounts to a plumbing problem? The people who should be able to answer that question are physicists. They use Fourier's equation every single day. It is as fundamental to modern physics as addition. And most of them, if you ask why it works on everything, will tell you it is a useful technique, a mathematical convenience, a tool. They will not tell you what the equation implies about the nature of reality, because the implication is uncomfortable. It suggests that the universe is not a collection of objects that can be described by mathematics. It suggests that the universe might be the mathematics, and that is a claim that makes physicists very nervous. I want to start with the man himself, because the way his life intersected with his discovery is one of those stories that feels like it was written by someone with a dark sense of humor. Jean-Baptiste Joseph Fourier was born on March 21st, 1768, in Auxerre, about 100 miles southeast of Paris. His father was a master tailor. There is almost nothing known about his mother, except that she gave birth to 12 children and died when Joseph was 9 years old. His father died the year after. 12 children, no parents, no money. The local bishop arranged for Joseph to attend the École Royale Militaire of Auxerre, a military academy run by Benedictine monks. And this is where the first strange detail appears. The boy was consumed by mathematics, not interested, not talented, consumed. He finished all 6 volumes of Bezout's mathematics course by the age of 14, and he studied at night after the other students had gone to sleep by collecting the discarded ends of candles and melting them together to make new ones. Multiple biographers describe this: the orphaned son of a tailor, sitting alone in an empty schoolroom by the light of recycled candle wax, teaching himself mathematics that was not in his curriculum. He wanted to join the artillery or the engineering corps, the 2 branches of the French military that were open to talent rather than birth. He was rejected, not because of his ability, because he was not noble. The scientific corps required noble blood. His mathematics teacher wrote, with evident frustration, that it was a shame Fourier was not of noble birth, because his talent was exceptional. So here is a pattern that is going to repeat itself across Fourier's entire life. A man with extraordinary ability being blocked by institutions that could not accommodate what he was. He drifted toward the priesthood, entering the Benedictine Abbey of Saint Benoît-sur-Loire in 1787. He was 21 years old and already restless. There is a letter from this period written to a friend that I think tells you everything you need to know about who Fourier was. He wrote that yesterday was his 21st birthday and that at that age, Newton and Pascal had already acquired many claims to immortality. He was not making a casual comparison. He was measuring himself against the greatest minds in history and finding himself behind schedule. He never took religious vows. He never became a priest because 1789 arrived and the revolution changed everything. Fourier threw himself into revolutionary politics with the same intensity he brought to mathematics. He joined a local revolutionary committee in Auxerre, wrote speeches about equality and liberty, and initially believed the revolution would create a more just society. But the terror changed his mind. When the executions began, when the guillotine became the primary instrument of political discourse, Fourier did something that took genuine physical courage. He publicly defended people who had been condemned. In Orleans, he intervened on behalf of victims of the terror, speaking against the very committee he had joined. And for this, in July of 1794, he was arrested. He was imprisoned and expected to die. He wrote to Robespierre himself, appealing for clemency. Robespierre did not respond. And here is where the dark humor of history intervenes. On July 28, 1794, Robespierre was overthrown and executed. The Thermidorian reaction swept through France. Fourier was released. But then, in a twist that borders on absurdity, he was arrested again almost immediately. This time, accused of being a Robespierre supporter, the very man whose silence had nearly cost him his head. It took interventions from Lagrange, Monge, and a group of his former students to get him released a second time. Think about that for a moment. The man who would write the most consequential equation in the history of applied mathematics was at age 26, sitting in a cell in revolutionary France, waiting to find out if the political winds would kill him or spare him. The equation that runs your phone, your Wi-Fi, your MRI machine, your entire digital life almost did not exist because a committee of politicians could not decide whether its author was too revolutionary or not revolutionary enough. By 1795, Fourier had entered the École Normale in Paris as its most brilliant student. His teachers were the giants of French mathematics. Lagrange, who Fourier would later call the first among European men of science. Laplace, whose celestial mechanics had rewritten astronomy. Monge, the founder of descriptive geometry. Fourier rose fast. By 1797, he held Lagrange's former chair of analysis and mechanics at the École Polytechnique. He was 30 years old, a professor at the most prestigious technical institution in France, and he had not yet done the work that would make him immortal. That required Napoleon and Egypt, and an obsession with heat that may have eventually killed him. In 1798, Gaspard Monge, who had become Fourier's mentor, recruited him for Napoleon's Egyptian campaign. This was partly a military invasion and partly a scientific expedition, a strange hybrid that tells you a great deal about Napoleon's ego. He brought along 167 scholars, scientists, and engineers, the intellectual cream of France, alongside 38,000 soldiers. Fourier was among them. When the French fleet was destroyed by Admiral Nelson at the Battle of the Nile on August 1, 1798, stranding the entire army in North Africa with no way home, Fourier did not panic. He became indispensable. He was elected secretary of the Institut d'Egypte, organized munitions workshops, established educational institutions, conducted diplomatic negotiations with local leaders, and oversaw the archaeological explorations that would eventually fill 21 volumes of the monumental Description de l'Égypte. Napoleon grew to rely on him so completely that Fourier became, in effect, the civilian governor of much of occupied Egypt. There is a detail from this period that I think matters. Egypt was hot, brutally, relentlessly hot, and Fourier, who would later become obsessed with warmth, appears to have thrived in it. He did not complain about the heat the way other members of the expedition did. He seemed to absorb it, to need it. When he returned to France in 1801, the cold of European winters hit him like a physical assault. Something had changed. Whether it was a medical condition contracted in Egypt, possibly myxedema from severe hypothyroidism, or whether the years in North African heat had permanently recalibrated his body's thermostat, he was never warm again. Napoleon, who never asked permission and never accepted refusal, appointed Fourier prefect of the department of Isère, based in Grenoble. Fourier did not want the job. He wanted to stay in Paris, near the intellectual community, near the mathematics. Napoleon did not care. Fourier was too useful as an administrator to waste on equations, and so Fourier governed, and he was, against all expectation, for a mathematician thrust into provincial bureaucracy, extraordinary at it. He drained approximately 80,000 square kilometers of malarial swamps in the Isère Valley, a public health intervention that saved thousands of lives. He planned a major highway from Grenoble to Turin across the Alps. He navigated the vicious local politics of post-revolutionary France with a diplomatic finesse that his colleagues in Paris found surprising. Napoleon rewarded him with a barony, but the relationship between the two men was never simple. There was always an element of coercion. Napoleon needed Fourier. Fourier needed Napoleon's protection. And when Napoleon's empire began to collapse, Fourier was caught in the wreckage. When Napoleon abdicated in 1814, Fourier desperately tried to avoid meeting him on the road to exile, taking a different route out of Grenoble at the last moment. When Napoleon returned from Elba the following year and marched on Grenoble in March of 1815, Fourier tried to rally the city's defenses, realized it was futile, and fled through one gate as Napoleon entered through another. It was farcical and terrifying in equal measure. Fourier later talked his way back into Napoleon's favor, was briefly appointed prefect of the Rhône in Lyon, then resigned in protest at the regime's increasing brutality. Napoleon, impressed by Fourier's spine even when it was directed against him, granted him a pension of 6,000 francs to begin on July 1st, 1815. Napoleon was defeated at Waterloo on June 18th. The pension was never paid. But I have gotten ahead of the story, because it was during those years in Grenoble, around 1804, long before Napoleon's fall, that Fourier turned his attention to the problem that had been quietly consuming him since Egypt: heat. How heat moves, how warmth spreads through solid objects. This was not a glamorous problem. It was not celestial mechanics or electromagnetism or the orbits of planets. It was about metal bars getting warm. But Fourier's obsession with heat was not purely intellectual. It was physical. The cold of post-Egypt France tormented him. He kept his rooms heated to temperatures that made visitors physically uncomfortable. He wrapped himself in heavy clothing and blankets even in summer. He lived, as one contemporary described it, swathed like a mummy in his overheated quarters. The man who would mathematically master the flow of heat was himself a prisoner of it. The problem, Fourier said himself, seems, on its surface, almost boring. You have a solid object, one part of it is hotter than another. How does the heat spread? What is the temperature at any given point at any given time? Before Fourier, the mathematics of heat was essentially non-existent. Isaac Newton had proposed a law of cooling that described how a hot object loses heat to its surroundings, but it was an empirical approximation, not a theory of how heat moves through the interior of a solid. The great mathematicians of the 18th century, Euler, D'Alembert, Daniel Bernoulli, had fought bitterly over the vibrating string problem, which involved similar mathematics, but nobody had systematically attacked heat conduction. Fourier's approach was not what a trained mathematician would have chosen. He was, remember, a physicist and an administrator, not a product of the pure mathematician's tradition. He did not start from axioms and deduce consequences. He started from physical intuition and forced the mathematics to follow. He imagined a thin metal bar heated at one end and asked how the temperature distribution would evolve over time. He derived what we now call the heat equation, a partial differential equation that relates the rate of temperature change at a point to the curvature of the temperature profile at that point. This equation was itself a significant contribution, but it was his method of solving it that detonated the controversy. His method was to assume that the temperature distribution, whatever its shape, could be written as a sum of sine and cosine functions, not because there was a mathematical proof that this was valid, not because it was an established technique, but because when you plug sines and cosines into the heat equation, they separate beautifully. Each sinusoidal component decays at a rate proportional to the square of its frequency. High-frequency components, the sharp details, die out quickly. Low-frequency components, the broad gradual variations, persist. This is why a hot spot on a metal bar does not stay sharp. It smooths out. The high-frequency Fourier components of the initial temperature profile are the first to decay. Fourier saw this and realized that if you could decompose any initial temperature distribution into sines and cosines, you could solve the heat equation for each component independently and add the solutions together. The mathematics was elegant. The physics was intuitive. The only problem was the central assumption. Could any temperature distribution, any arbitrary function, really be written as a sum of sines and cosines? Fourier said yes, and he was about to walk into a room full of people who would tell him he was wrong. On December 21st, 1807, Fourier stood before the Institut de France and presented a memoir titled On the Propagation of Heat in Solid Bodies. The room contained some of the most formidable mathematical minds that have ever lived. Lagrange was there, Laplace was there, Monge was there, Lacroix was there. These were the review committee, the gatekeepers of French mathematical orthodoxy. And what Fourier told them made at least one of them physically angry. His claim was this: any function whatsoever, any shape you can draw on a piece of paper, no matter how jagged, how discontinuous, how full of sharp corners and sudden jumps, can be written exactly as a sum of smooth, rolling sine and cosine waves, not approximately, exactly. A perfect square wave, with its sharp 90-degree corners, can be built from the smoothest curves in mathematics. A sawtooth, a staircase function, a function that jumps from one value to a completely different value with no transition at all. According to Fourier, every single one of these could be decomposed into sines and cosines. Now I need you to understand why this claim was so explosive. Sine waves are the smoothest, most regular curves that exist. They have no corners, they have no jumps, they are infinitely differentiable. meaning you can take their derivative as many times as you want, and you will always get another smooth, well-behaved function. The idea that you could add up smooth curves and get a sharp corner was to the mathematicians in that room roughly as intuitive as claiming you could build a brick wall out of water. Smooth things should sum to smooth things. That was not a controversial position. That was what the mathematics appeared to demand. And here is the critical detail. Lagrange, a man Fourier himself called the first among European men of science, the most respected mathematician alive, said no. He did not express polite skepticism. He did not suggest further investigation. He declared Fourier's central claim absurd. Lagrange had worked with trigonometric series since the 1750s, vibrating string controversy. He knew these series could represent certain well-behaved functions, but any function, including discontinuous ones, impossible. And Lagrange was 71 years old. He had been the dominant voice in European mathematics for decades. And when he said something was impossible, the conversation was over. The paper was not published. I want to be precise about this, because the mechanism of suppression matters. The Institute did not reject the paper outright. They did something more insidious. They sat on it. No publication, no refutation, just silence. Laplace joined Lagrange's objection in 1808. The paper entered a bureaucratic limbo where it would remain for years. Then, in a move that feels almost deliberately humiliating, the Institute announced that the propagation of heat would be the subject of its 1811 mathematics prize. Fourier resubmitted his work with substantial additions. The prize committee was Lagrange, Laplace, Malus, Hauy, and Legendre, and they awarded him the prize. But their report is one of the most precisely damning documents in the history of mathematics. They wrote that the work still left something to be desired on the score of generality and even rigor. They gave him the prize and insulted his methods in the same breath. And still, the paper was not published. Meanwhile, two other mathematicians, Poisson and Biot, began publishing their own work on heat theory, in some cases using methods that bore a suspicious resemblance to Fourier's unpublished results. Fourier was furious. He wrote a response that was never published, but survives in his letters. And it is devastating. He wrote that if they had established a principal element of the theory of heat by fine experiments, they would have the right to judge his work. But one does not extend the bounds of science by presenting, in a form said to be different, results which one has not found oneself, and above all, by forestalling the true author in publication. That is a man accusing his colleagues of intellectual theft, and the institution that should have protected his priority was the same institution that refused to publish his paper. Fourier's masterwork, the Théorie analytique de la chaleur, was finally published in 1822, 15 years after the original presentation. 9 years after Lagrange's death, Lagrange never accepted Fourier's claim. He died believing it was wrong. The book opens with one of the most beautiful and ambitious declarations in the history of science. Fourier wrote that the deep study of nature is the most fertile source of mathematical discoveries. Not that mathematics illuminates nature, though it does. That nature illuminates mathematics, that the physical world is the origin of mathematical truth, not the other way around. He continued by arguing that mathematical analysis is as extensive as nature itself, that it defines all perceptible relations, and that there cannot be a language more universal and more simple, more free from errors and obscurities. That last phrase haunts the history of science because it turned out to be more prophetic than even Fourier could have imagined. The language he developed for heat in metal bars would turn out to be universal in a sense that is almost literally true. The book also contains the first systematic use of dimensional analysis, the insistence that physical equations must balance dimensionally. This seems elementary now, but it was not established practice before Fourier formalized it. He was, in many ways, the first modern mathematical physicist, a person who insisted that mathematics must be grounded in physical reality, and that physical reality must be expressible in rigorous mathematics. He occupied a space between the pure mathematicians who found his methods insufficiently rigorous and the experimental physicists who found his abstractions unnecessary. That middle ground, the territory of mathematical physics, is where most of modern science now lives. And here is the part that should make you angry, because the resolution of this story is not that Fourier was proven right in some simple, clean way. The resolution is far stranger than that. The attempt to determine whether Fourier was right or wrong generated an intellectual earthquake that restructured the foundations of mathematics itself. The first major advance came from a young German mathematician named Peter Gustav Lejeune Dirichlet, who Fourier had personally mentored during the older man's final years in Paris. In 1829, Dirichlet published the first rigorous convergence theorem for Fourier series. What are now called the Dirichlet conditions specify exactly when a Fourier series converges. The function must be absolutely integrable, must have finitely many maxima and minima per period, and must have finitely many discontinuities of finite magnitude. At points where the function is continuous, the series converges to the function's value. At points of discontinuity, it converges to the average of the left and right limits. This vindicated Fourier for essentially every function that arises in physics, while acknowledging that pathological edge cases exist. But there was a deeper problem that Dirichlet's work exposed. When you start talking about discontinuous functions with jumps and breaks, you need to be extremely precise about what you mean by an integral. The old intuitive notion was not rigorous enough. Bernard Riemann, Dirichlet's student at Göttingen, chose Fourier series as the subject of his 1854 habilitation thesis, and was driven by the demands of Fourier's mathematics to invent what we now call the Riemann integral. The definition of integration that is taught in every calculus classroom in the world was created because Fourier's equation required it. Mathematics did not have the tools to handle what Fourier had proposed, so mathematics had to build new tools. And it gets worse, because the question Fourier raised, whether any function can be represented by a trigonometric series, kept producing monsters. In 1873, a mathematician named Paul Dubois-Raymond proved that there exists a continuous function whose Fourier series diverges at a point. A continuous function, no jumps, no corners, just a smooth, unbroken curve. And its Fourier series fails to converge at least one point. This was deeply unsettling. It meant that Fourier's claim had limits even within the realm of well-behaved functions. The question of exactly which functions have convergent Fourier series became one of the central open problems in analysis, and it would not be fully resolved for nearly another century. But the most extraordinary consequence of Fourier's work was something nobody could have predicted. In the early 1870s, a mathematician named Georg Cantor was working on the uniqueness problem for trigonometric series. The question was, if two different Fourier series converge to the same function everywhere, must the series be identical? Cantor proved that yes, they must, except possibly on certain exceptional sets of points. And in characterizing those exceptional sets, in trying to understand exactly how strange they could be, Cantor was led to define derived sets, transfinite ordinals, and different sizes of infinity. Set theory, the foundation on which all of modern mathematics is built, was born from a question about Fourier series. This is not a metaphorical connection. Cantor's first papers on set theory are explicitly motivated by questions about trigonometric series representations. I need to pause here because I think the weight of this does not land properly if I move past it too quickly. The most important mathematical framework of the 20th century, the language in which virtually all of modern mathematics is written, was created because an orphaned tailor's son made an unprovable claim about sine waves in 1807, and the attempt to determine whether he was right required inventing an entirely new conception of infinity. That is not how we are taught the history of mathematics. We are taught that set theory was created by Cantor as an abstract investigation into the nature of the infinite. The fact that it was born from Fourier analysis, from a concrete question about whether sine waves can represent arbitrary functions, is one of the most consequential omissions in the standard curriculum. Think about the chain of causation. Fourier asks whether any function can be written as a sum of sines. Lagrange says no. The question is left open for decades. Cantor, working on the uniqueness problem for trigonometric series, needs to characterize certain exceptional sets of points. To do this, he invents derived sets. To understand derived sets, he needs transfinite ordinals. To formalize transfinite ordinals, he needs a theory of infinite sets. And suddenly, he is face to face with the discovery that there are different sizes of infinity, that the real numbers are uncountably infinite, while the integers are merely countably infinite, and that the structure of the infinite is far richer and stranger than anyone had imagined. All of this because Fourier wanted to solve the heat equation and proposed using sine waves. The thread from a metal bar in Grenoble to the foundations of modern mathematics is unbroken and direct, and almost nobody teaches it that way. The final chapter of this mathematical saga came in 1966, when the Swedish mathematician Lennart Carlsson proved what is now called Carlsson's theorem. The Fourier series of any square integrable function converges pointwise almost everywhere. The proof was so difficult, so technically demanding, that even simplified versions remain notoriously hard to follow. Carlsson himself had initially set out to find a counterexample, to prove that Fourier was wrong. He later described how the counterexample had to satisfy so many properties that the properties started to contradict each other, and he realized the conjecture must be true. He spent years working on the proof. It was, by the account of other mathematicians, one of the great technical achievements of 20th century analysis. So, here is the scorecard. Fourier's claim, made in 1807, dismissed by Lagrange, suppressed for 15 years, was not fully resolved until 1966, 159 years, and in the process of resolving it, mathematics had to invent rigorous integration, discover set theory, develop measure theory, and produce one of the hardest proofs in the history of analysis, a claim about heat in a metal bar. But here is what I want you to hold on to as we go forward. Because the mathematical drama, as extraordinary as it is, is not the real story. The real story is what happened when engineers got hold of the equation, because the mathematics told us that Fourier's decomposition works. What nobody expected was how universally it works, and the universality is the part that should keep you up at night. For 150 years after Fourier, his decomposition remained an elegant piece of mathematics that was computationally impractical for anything large. The reason is arithmetic. If you want to compute the discrete Fourier transform of n data points, the straightforward method requires n-squared operations. For 1,000 data points, that is 1,000,000 calculations, manageable. For 1,000,000 data points, that is 1,000,000,000,000 calculations, not manageable. For 1,000,000,000 data points, at 1 nanosecond per operation, the computation would take 31 years. The equation worked in theory, but it was locked behind a wall of brute force arithmetic that no machine on Earth could climb fast enough. And then, in 1965, 2 men published a 4-page paper that changed everything. James Cooley of IBM and John Tukey of Princeton described what is now called the fast Fourier transform, an algorithm that reduces the computation from n-squared to n log n operations. For 1,000 points, that is roughly 10,000 operations instead of 1,000,000, 200 times faster. For 1,000,000 points, it is about 20 million instead of 1,000,000,000, roughly 100,000 times faster. For 1,000,000,000 points, the 31-year calculation collapses to about 15 seconds. A 4-page paper made digital civilization computationally possible. But here is the part of this story that was classified. The real motivation for the FFT was not scientific curiosity, it was nuclear espionage. In 1963, at a meeting of President Kennedy's Science Advisory Committee, a physicist named Richard Garwin learned that Tukey had been developing a faster method for computing Fourier transforms. Garwin immediately recognized its military value. The United States had been trying to monitor Soviet underground nuclear tests using seismometer arrays, but processing the seismic data required enormous numbers of Fourier transforms that were computationally infeasible. Garwin connected Tukey with Cooley at IBM, but Garwin deliberately kept Cooley in the dark about the real application. Cooley was told the algorithm was needed for analyzing helium-3 crystal structures. He wrote the Fortran code on an IBM 7094 mainframe, and the FFT was first demonstrated in 1964. Once the algorithm existed, it was immediately deployed to process seismometer data from sensors planted around the Soviet Union. The FFT enabled locating underground nuclear explosions to within 15 kilometers, a capability that was essential to the Partial Nuclear Test Ban Treaty. The most important algorithm in the history of computation was developed as a tool of Cold War surveillance. Cooley did not learn the true purpose of his work for years. And then there is the part that makes the whole story feel like a cosmic joke. The FFT was not new. Carl Friedrich Gauss, arguably the greatest mathematician who ever lived, had developed an equivalent method around 1805, 2 years before Fourier even presented his memoir. Gauss used it to interpolate the orbital trajectories of the asteroids Pallas and Juno. He wrote it in Latin. It was published only after his death, in 1866, in the 3rd volume of his collected works, and nobody noticed. A connection between Gauss's method and the modern FFT was not recognized until 1984, when Heidemann, Johnson, and Burrus published a paper tracing the historical precedents. There were other precursors too. Clairaut in 1754, Runge in 1903, Danielson and Lankos in 1942. Every one of them applied some version of the key recursive insight without recognizing its computational complexity. The most important algorithm in modern technology was invented, forgotten, reinvented, classified, and only then made public. If that does not make you angry about how knowledge actually propagates, I do not know what will. Once the FFT made Fourier analysis computationally practical, the equation began to colonize every domain of technology. And I want to be careful here, because I am not going to give you a list of applications. What I am going to do is show you how each application is a failed attempt to explain why this equation works on everything. Because every time you think you have understood why it works in one domain, it shows up in a completely different domain where the same explanation should not apply. Start with sound. When you listen to an MP3, you are listening to Fourier's equation. The MP3 standard uses a variant called the modified discrete cosine transform to decompose audio into its frequency components. Your ear does something remarkably similar, by the way. The cochlea physically separates sound into frequency bands, which is itself a biological Fourier transform. The MP3 encoder takes that frequency decomposition and then applies a psychoacoustic model to throw away the parts your brain cannot perceive. Frequencies masked by louder nearby sounds, extremely high frequencies above the threshold of hearing. The result is a compression ratio of roughly 10:1. A 42 megabyte uncompressed song shrinks to about 3.75 megabytes at 128 kilobits per second. Karl-Heinz Brandenburg of the Fraunhofer Institute developed the standard using Suzanne Vega's Tom's Diner as his primary test track because the simple vocal recording was particularly good at revealing compression artifacts. You might think you understand why Fourier analysis works on sound. Sound is waves. Sine waves represent pure tones. Of course, you can decompose sound into sine waves. That makes intuitive sense. But then the equation shows up in images. JPEG compression takes a photograph, divides it into 8 by 8 pixel blocks, and applies a two-dimensional discrete cosine transform to each block. This converts spatial information, the brightness of pixels, into spatial frequency information. Low frequencies represent broad, gradual changes in brightness. High frequencies represent sharp edges and fine detail. The encoder then aggressively quantizes the high-frequency coefficients, throwing away fine detail that the human eye is least sensitive to. At typical settings, JPEG achieves 10:1 compression with minimal visible degradation. The blocking artifacts you see in over-compressed images are literally the boundaries of those 8 by 8 Fourier domain blocks becoming visible. Several billion JPEG images are created every single day. An estimated 14.3 trillion photographs exist worldwide, and the vast majority are in JPEG format. Now this is where the easy explanation starts to break. Sound is waves. Fine. But a photograph is not a wave. A photograph is a two-dimensional grid of colored dots. There is nothing obviously periodic or wave-like about a picture of your dog, and yet the same mathematical decomposition, breaking something into sine and cosine components, works on images just as well as it works on audio. Why? You could say that spatial patterns can be described by spatial frequencies, that brightness variations across an image are analogous to amplitude variations across a sound wave. And that is true. But it is a description of the fact, not an explanation of it. Why should spatial brightness variations and temporal air pressure variations be decomposable by the same equation? I want to sit with this question for a moment, because I think it gets brushed past too quickly. When we say the Fourier transform works on images, what we mean is that any two-dimensional pattern of brightness values can be perfectly represented as a sum of two-dimensional sinusoidal gratings at various frequencies, orientations, and phases. A vertical stripe pattern is a single Fourier component. A horizontal stripe pattern is another. A checkerboard is a combination, and somehow every photograph ever taken, every landscape, every portrait, every chaotic jumble of visual information can be reconstructed from a finite set of these perfectly regular gratings. The visual complexity of the entire world reduces to combinations of stripes. That is not obvious. That is not intuitive. That is bizarre. And the strangeness compounds when you realize that your own visual system appears to do something similar. Neurons in the primary visual cortex, area V1, are tuned to respond to oriented gratings at specific spatial frequencies. Your brain decomposes visual input into something that resembles a Fourier representation before you consciously perceive the image. David Hubel and Torsten Wiesel won the 1981 Nobel Prize in Physiology or Medicine for discovering this. The mathematics that Fourier invented for heat conduction appears to be implemented biologically in your visual cortex. Not because evolution read Fourier's paper, but because the decomposition is apparently so fundamental that biological neural networks converge on it independently. And then it gets worse, because the equation does not just compress your music and your photographs, it carries your voice. Every Wi-Fi connection you have ever used, every 4G phone call you have ever made, every 5G data stream you have ever received, runs on a technology called orthogonal frequency division multiplexing, OFDM. And the way it works is this. The transmitter takes the data you want to send and performs an inverse fast Fourier transform to encode that data across thousands of closely spaced frequency subcarriers. The receiver then performs a forward FFT to decode them. This is not a metaphor, and I want to make sure that is clear. Your phone is not using something inspired by Fourier analysis. Your phone is literally computing Fourier transforms. The transmitter computes an inverse transform. The receiver computes a forward transform, thousands of times per second. Every time you load a web page, every time you stream a video, every time you send a text message, the Fourier transform is being computed in real time by the chip in your hand. As of 2025, there are approximately 23.3 billion Wi-Fi devices in active use worldwide. There are 9.1 billion mobile cellular subscriptions globally, more than the total human population, because many people have multiple subscriptions. The Wi-Fi Alliance estimates that Wi-Fi alone contributes $4.9 trillion to the global economy annually. Every one of those devices, every one of those connections, every one of those trillions of dollars depends on the Fourier transform operating continuously and in real time. I spent an unreasonable amount of time trying to estimate how many FFT operations are performed globally per second. The number is not precisely calculable, but the order of magnitude is somewhere in the quadrillions. thousands of trillions of Fourier transforms every second on a planet where the equation was suppressed for 15 years because a 71-year-old mathematician thought the central claim was absurd. Think about what that means. Not the scale. Although the scale is staggering, think about what it means that the same equation governs how sound is compressed, how images are stored, and how radio signals are transmitted. These are three completely different physical phenomena: air pressure variations, spatial brightness patterns, electromagnetic wave propagation. They have nothing in common except that they all yield to the same decomposition into sine and cosine components. It is as if you discovered that the same key opens every lock on Earth, not because someone designed it that way, but because every lock happens to have the same internal structure. And that is strange. That should feel strange to you, because it suggests something about the structure of reality that goes far beyond mathematical convenience. But that equation does not just carry information and compress files. It also looks inside your body. And the way it does this is, I think, the most beautiful application of mathematics in the history of medicine. When you lie inside an MRI machine, the scanner does not take a photograph of your insides. That is the common misconception, and it hides something much stranger. What the scanner actually does is place you inside an extraordinarily powerful magnetic field, typically 1.5 to 3 Tesla, roughly 30 to 60,000 times stronger than the Earth's magnetic field. This field aligns the hydrogen atoms in your body, which are mostly in water molecules, along a single axis. Then the machine hits you with a precisely tuned radio frequency pulse that knocks those hydrogen atoms out of alignment. When the pulse stops, the atoms relax back to their aligned state, and as they do, they emit tiny radio signals. Here is the critical part. The scanner does not collect these signals as an image. It collects them as data in what physicists call K-space. K-space is the spatial frequency domain. The center of K-space encodes broad, low-frequency contrast information, the general shapes and brightness levels. The periphery encodes high-frequency information, fine edges, and sharp details. The raw data sitting in the MRI scanner's memory looks nothing like a picture of your brain or your knee or your spine. It looks like an abstract pattern of frequency coefficients. The image that your radiologist reads is produced by performing a two-dimensional inverse Fourier transform on the K-space data. Every MRI image you have ever seen, every diagnosis that was made from one, every tumor that was detected or ruled out was constructed by Fourier's equation, converting frequency domain data into spatial domain data. Paul Lauterbur and Peter Mansfield shared the 2003 Nobel Prize in Physiology or Medicine for developing this technique. Today, approximately 50,000 MRI machines operate worldwide, performing somewhere between 100 million and 150 million scans annually. Around 40 million of those are in the United States alone. The global MRI equipment market exceeds $7 billion, and every single scan depends on the same equation that was rejected in 1807. CT scanning tells a similar story, but through a different mathematical door. When a CT scanner rotates around your body, it takes X-ray projections from hundreds of angles. Each projection is a one-dimensional shadow of a two-dimensional slice. And here is where a result called the Fourier slice theorem enters. The theorem states that the one-dimensional Fourier transform of a projection at any given angle is exactly equal to a radial line through the two-dimensional Fourier transform of the original tissue. So by collecting projections at many angles, computing their individual Fourier transforms, and assembling those transforms into a complete two-dimensional frequency map, you can perform a single inverse Fourier transform and recover the original cross-sectional image. This is called filtered back projection, and it is the mathematical core of CT imaging. Roughly 375 million CT scans are performed annually worldwide, with over 80 million in the United States alone. Every one of them is a Fourier reconstruction. So the same equation that compresses your music, stores your photographs, and carries your phone calls also constructs the medical images that save lives every day. And I want you to notice something. The physical phenomena keep changing. Sound is vibrations in air. Images are patterns of reflected light. Radio signals are electromagnetic waves. MRI data is nuclear magnetic resonance from hydrogen atoms. X-ray projections are differential absorption of high-energy photons through tissue. These are completely different physical processes. They have different underlying mechanisms, different energy scales, different everything, and they all yield to the same decomposition. It is as if reality has a preferred language, and that language is sine waves. I want to push this further because the equation does not stop at the boundary of your body. It reaches into the fabric of space-time itself. In 2002, a 22-year-old British computer science student named Avery Lee Chun Wang published a paper describing how to identify a song from a few seconds of noisy audio. The technique, which became Shazam, works like this. The app captures a short clip of ambient sound, applies the short-time Fourier transform to produce a spectrogram, a visual map of which frequencies are present at each moment, identifies the loudest frequency peaks in that spectrogram, generates combinatorial hashes from pairs of those peaks, and matches the hashes against a database of over 40 million songs. The system has now surpassed 100 billion song recognitions worldwide, roughly 12 for every human being on Earth. Apple acquired Shazam for $400 million in 2018. The entire system is built on Fourier analysis. Active noise cancellation in headphones uses the same underlying principle. Ambient sound is captured by external microphones, decomposed into frequency components via FFT, and a mirror image, anti-phase signal, is generated and played through the speaker to cancel the noise through destructive interference. The technique reduces ambient noise by 20 to 30 decibels and works best at low frequencies where wavelengths are long enough for the anti-phase signal to align accurately. The global noise-cancelling headphone market exceeded $12 billion in 2204. Those are commercial applications. Consumer technology, the equation's reach goes further. On September 14th, 2015, at 5:51 in the morning Eastern Time, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, one in Hanford, Washington, and one in Livingston, Louisiana, recorded a signal that swept upward in frequency from 35 to 250 Hz over approximately 0.2 of a second. It was the gravitational wave signature of two black holes, one of 36 solar masses and one of 29 solar masses, spiraling into each other at roughly half the speed of light and merging into a single black hole of 62 solar masses. The missing 3 solar masses had been radiated away as gravitational wave energy. More power output in that fraction of a second than all the stars in the observable universe combined. I want to make sure the scale of what LIGO was measuring registers properly. The gravitational wave compressed and stretched the 4-kilometer detector arms by a distance of approximately 10 to the negative 18 meters. That is 1,000th the diameter of a proton. If you scale the detector up to the distance from the Earth to the nearest star, Alpha Centauri, roughly 4 light years away, the gravitational wave would change that distance by about the width of a human hair. LIGO measures changes in length that are smaller than anything that has ever been measured in the history of experimental physics. The noise floor of the instrument, the random jitter from thermal vibrations of the mirrors, from seismic rumbles in the Earth, from quantum fluctuations in the laser light itself, is vastly larger than the signal. Extracting the gravitational wave from that noise is like detecting the sound of a single human heartbeat in a stadium full of screaming fans during a thunderstorm. And the tool that makes it possible is the Fourier transform. The raw strain detected by the interferometers was approximately 10 to the negative 21, a change in the length of the 4-kilometer detector arms of about 1,000th the diameter of a proton. To extract this signal, the LIGO team used a technique called matched filtering, which is fundamentally a Fourier domain operation. They computed the FFT of the detector data, compared it against a library of template waveforms in the frequency domain, and identified the signal with a matched filter signal-to-noise ratio of 24 and a false alarm rate of less than 1 event per 203,000 years. Without Fourier analysis, the most important astronomical observation of the 21st century would have been invisible. A ripple in the geometry of space-time detected by a technique invented for heat conduction in metal bars. And it goes deeper than detection. In April of 2019, the Event Horizon Telescope collaboration released the first image of a black hole, the supermassive object at the center of the galaxy Messier 87. The EHT is not a single telescope. It is a network of radio telescopes spanning the globe from Hawaii to Spain to the South Pole, linked together through a technique called very long baseline interferometry. Each pair of telescopes in the array does not capture a pixel of the image. It measures one Fourier component of the sky brightness at the angular frequency corresponding to the baseline separation between those two telescopes. As the Earth rotates, the baseline between each pair changes, sweeping out additional Fourier components. The complete set of measured Fourier components is assembled into a partial frequency domain representation of the sky, and the image is reconstructed by inverting the Fourier transform. Over 1 petabyte of raw frequency domain data was reduced to a single image of a ring of light surrounding a dark shadow. That image was a Fourier reconstruction. The first photograph of a black hole was not taken by a camera. It was computed by Fourier's equation. Spectral analysis in astronomy uses the same mathematics to identify the chemical composition of stars through their unique frequency fingerprints, and to detect exoplanets through the radial velocity method, where Fourier analysis of Doppler shifted starlight reveals the tiny periodic wobbles caused by the gravitational tug of orbiting planets. Over 1,100 exoplanets, roughly 19% of all confirmed discoveries, have been found this way. I need to stop here and make sure the weight of this registers. The same equation, the exact same mathematical operation, compresses your music, stores your photographs, carries your phone calls, constructs medical images of your internal organs, identifies songs from noisy audio clips, cancels ambient noise in your headphones, detects gravitational waves from colliding black holes, photographs the shadow of a supermassive black hole, identifies the chemical elements in distant stars, discovers planets around other suns. This is one equation, written by one man, for heat in a metal bar, and every explanation I have given you so far for why it works is incomplete. It works on sound because sound is waves. It works on images because spatial patterns have spatial frequencies. It works on radio because radio is electromagnetic waves. It works on MRI because nuclear magnetic resonance produces frequency domain data. It works on gravitational waves because space-time distortions propagate. As waves, each explanation is local. Each explanation is specific to one domain. But there is no explanation for why all of these domains share the same mathematical structure. No one has adequately explained why the same decomposition into sine and cosine components works on air pressure, pixel brightness, electromagnetic resonance, and the geometry of space-time, unless the explanation is not about the domains at all, unless the explanation is about reality itself, unless reality is, at some fundamental level, made of the same stuff that Fourier's equation decomposes. And that is where quantum mechanics enters the story. And that is where the equation stops being a tool and starts being the thing itself. I want to be very precise about what I am about to say, because it is easy to slide into vagueness here, and the actual claim is much more specific and much more disturbing than the vague version. In quantum mechanics, every particle is described by a wave function. You were probably taught that this wave function gives you the probability of finding the particle at a particular location. That is true, but it is incomplete in a way that hides the most important part. The wave function exists in two representations. There is the position space representation, which tells you the probability of finding the particle at different locations, and there is the momentum space representation, which tells you the probability of the particle having different momenta. These two representations are not independent descriptions. They are not two different theories. They are connected by a single mathematical operation. The Fourier transform, the wave function in position space, is the Fourier transform of the wave function in momentum space. And the wave function in momentum space is the inverse Fourier transform of the wave function in position space. They are Fourier pairs, connected by the de Broglie relation P equals h bar times k, where P is momentum, h bar is the reduced Planck constant, and k is the wave number. This is not an approximation. This is not an analogy. This is the mathematical structure of quantum mechanics. Position and momentum are Fourier conjugate variables. And here is where the equation reveals something that most physics education deliberately obscures. The Heisenberg uncertainty principle says you cannot simultaneously know a particle's exact position and its exact momentum. The more precisely you know one, the less precisely you can know the other. Delta x times delta p is greater than or equal to h bar over 2. You were taught this as a deep mystery of quantum mechanics. You were taught that it has something to do with the act of measurement disturbing the particle, or with the fundamental graininess of nature, or with some irreducible quantum weirdness that sets the subatomic world apart from the everyday. That is not what it is. The Heisenberg uncertainty principle is a mathematical theorem about Fourier transforms. The proof has nothing to do with physics. Nothing. It is a property of Fourier pairs. If you have any function and its Fourier transform, the product of their widths cannot be smaller than a fixed minimum. The more concentrated the function is, the more spread out its Fourier transform must be, and vice versa. This is true of sound waves. It is true of radio signals. It is true of any signal in any domain that can be Fourier transformed. A very short musical note has an inherently broad frequency spectrum. You cannot have a sound that is both perfectly localized in time and perfectly localized in frequency. That is not quantum mechanics. That is Fourier analysis. The uncertainty principle simply identifies the conjugate variables as position and momentum rather than time and frequency, and it gives a mathematical truth, physical teeth, through the de Broglie relation. I still do not know how to fully process this. The uncertainty principle, perhaps the most famous result in all of quantum mechanics, the thing that is presented in every textbook and every documentary as evidence that the quantum world is fundamentally strange and different from our everyday experience, is actually a general mathematical property that was true before quantum mechanics existed. It would be true in a universe with completely different physics, as long as that universe had Fourier transform pairs. It is not a discovery about nature. It is a discovery about mathematics that nature happens to obey. And this is where most people would stop and say something reassuring about how mathematics is a useful tool for describing the physical world. But I cannot stop here, because the next layer is worse. In quantum field theory, the modern framework that underlies all of particle physics, the Standard Model, and our deepest understanding of matter and forces, the Fourier transform is not applied to particles. It is particles. Here is what I mean. A quantum field, say the electromagnetic field, is defined at every point in space. To quantize it, to turn it from a classical field into a quantum one, you first decompose it into Fourier modes. You break the field into plane waves at every possible frequency and wave number. Each Fourier mode is then treated as an independent quantum harmonic oscillator. The creation operator for a photon, with wave vector k, written as a dagger of k, creates an excitation in that specific Fourier mode. What we call a photon is not an object that happens to be associated with a particular frequency. A photon is an excitation of a single Fourier mode of the electromagnetic field. The same is true for every particle in the Standard Model. An electron is an excitation of the electron field's Fourier mode. A quark is an excitation of the quark field's Fourier mode. A Higgs boson is an excitation of the Higgs field's Fourier mode. David Tong, whose Cambridge lectures on quantum field theory are among the most respected in the world, puts it directly. The field is primary, and particles are derived concepts, appearing only after quantization, and the quantization procedure is Fourier decomposition. I want to make sure the radicalism of this claim is not lost in the technical language. When you learned about particles in school, you were probably given the impression that particles are tiny objects, little billiard balls that bounce around and interact with each other. That picture is wrong. It has been wrong since the 1940s when quantum field theory was developed, but it persists in popular science because the real picture is harder to communicate and more disturbing to contemplate. The real picture is this. There is an electron field that pervades all of space. It is everywhere. It has a value at every point. When that field is in its lowest energy state, its ground state, there are no electrons anywhere. When a single Fourier mode of that field is excited by one quantum of energy, an electron appears with a definite momentum corresponding to the wave number of that mode. The electron is not a thing sitting in the field. The electron is the excitation. It is a ripple, a vibration, a specific frequency in the electron field, just as a specific musical note is a specific frequency in the air. And when the excitation is removed, the electron does not go somewhere else. It ceases to exist. The field returns to its ground state. There is no electron hiding behind a curtain waiting to reappear. There is only the field and its Fourier modes and the excitations of those modes that we call particles. This is not speculation. This is the standard framework of modern particle physics. Every prediction of quantum electrodynamics, the most precisely tested theory in the history of science, with predictions verified to 10 decimal places, is computed using this Fourier mode framework. When physicists at CERN discovered the Higgs boson in 2012, what they actually found was evidence that a particular Fourier mode of the Higgs field had been excited to the expected energy level. The discovery was announced in terms of a particle, because that is the language we use. But the mathematics underneath is a Fourier decomposition of a quantum field. Think about what that means. You are made of particles, electrons, quarks, photons mediating electromagnetic forces between them. Every atom in your body, every molecule, every cell is a structure built from quantum field excitations. And those excitations are Fourier modes. You are not an object that can be described by Fourier analysis. You are a pattern of Fourier modes. The distinction between described by and made of has collapsed. I want to come back to Fourier for a moment here, because the personal and the physical are not separate threads. They are the same thread running in both directions. A man who collected candle wax to study mathematics by stolen light, who was told he was not noble enough for the scientific corps, who was nearly guillotined twice, who was dismissed by the greatest mathematician alive, who waited 15 years for his paper to be published. That man did not merely invent a useful technique. He uncovered the vocabulary in which physical reality writes itself. And the people who told him he was wrong were not wrong because they were stupid. They were wrong because they could not imagine that mathematics had that kind of authority over the physical world. They thought the equation was a description. It turned out to be a constituent. And this raises a question that I think is the most important question in the philosophy of science, and it has never been adequately answered. In 1960, the Hungarian-American physicist Eugene Wigner published an essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. It is one of the most cited papers in the philosophy of physics. Wigner's central observation was that mathematical concepts developed for purely abstract reasons, with no physical application in mind, repeatedly turn out to be exactly the tools needed to describe physical reality. He called this unreasonable. He meant that there is no good explanation for why the universe should be describable by mathematics at all, let alone by mathematics that was developed independently of physical motivation. Fourier's equation might be the single most powerful example of Wigner's puzzle. It was developed for heat conduction. It now governs quantum mechanics, telecommunications, medical imaging, gravitational wave detection, cosmology, and the structure of matter itself. You could argue, as the mathematician Ivor Grattan Guinness has, that the effectiveness is quite reasonable, that all these domains share underlying linear partial differential equation structure. So of course, the same mathematical tools apply. But that just pushes the question back one level. Why does physical reality have linear PDE structure? Why are the fundamental equations of physics, Maxwell's equations, the Schrödinger equation, the wave equation, all linear? Why does superposition hold? Why can solutions be decomposed into independently evolving sinusoidal components? The MIT physicist Max Tegmark has proposed the most radical answer. In his 2007 paper, The Mathematical Universe, published in Foundations of Physics, Tegmark argues that mathematics is not merely effective at describing the physical world. He argues that the physical world is a mathematical structure, not that it is described by one, that it is one. If Tegmark is right, then Fourier's equation does not describe reality. It is a piece of reality. And sine waves are not useful fictions we impose on nature. They are what nature is made of. I want to take a detour here because I think there is a layer to this question that most people miss, and it connects back to something I said earlier about linearity. There is a mathematical fact about sine waves that is not well known outside of physics and engineering, and it is, I think, the closest thing we have to an explanation for why Fourier analysis works on everything. Sine waves are the eigenfunctions of the derivative operator. What that means is this. If you take the derivative of a sine wave, you get another sine wave. The same frequency, just shifted in phase and scaled in amplitude. The derivative of sine is cosine. The derivative of cosine is negative sine. You can differentiate a sine wave 100 times and you will always get another sine wave at the same frequency. No other function family has this property. Why does this matter? Because the fundamental equations of physics are differential equations. They involve derivatives. Newton's second law involves the second derivative of position. Maxwell's equations involve derivatives of electric and magnetic fields. The Schrödinger equation involves derivatives of the wave function. The heat equation involves the second derivative of temperature. When you feed a sine wave into any of these equations, the equation simplifies enormously because differentiation does not change the frequency. Each Fourier component evolves independently. You can solve for each one separately and add the solutions together. There is a second, complementary reason that sine waves pervade physics, and it is arguably even more fundamental. Virtually any physical system near a point of stable equilibrium behaves as a harmonic oscillator. If you expand any smooth potential energy function around its minimum using a Taylor series, the leading term is quadratic. A quadratic potential gives you a restoring force proportional to displacement, and the equation of motion for such a system is the harmonic oscillator equation, whose solutions are sines and cosines. A pendulum swinging through small angles, a weight bobbing on a spring, an atom vibrating in a crystal lattice, an electromagnetic field mode in a cavity. All of them, near equilibrium, oscillate sinusoidally. Stephen Strogatz of Cornell has written that every smooth oscillation is a sine wave, and that this is not an approximation, but a theorem. The world vibrates in sine waves, not because we choose to describe it that way, but because the mathematics of stability demands it. This is mathematically beautiful, but it raises the question one more level. Why are the fundamental equations of physics differential equations? Why are the laws of nature written in terms of derivatives? Why does nature care about rates of change and curvatures rather than, say, integrals or discrete operations or something we have not thought of? Nobody knows. That is not a rhetorical statement. Nobody knows why the laws of physics take the form of differential equations. It is treated as a given, as the starting point of physics, not as something requiring explanation. But if the laws were not differential equations, then sine waves would not be eigenfunctions of those laws, and Fourier analysis would not work. The universality of Fourier's equation is, in the end, a consequence of the fact that the universe chose to write its laws in terms of derivatives. And the question of why it made that choice, if choice is even the right word, is one of the deepest unanswered questions in all of science. I am not telling you Tegmark is right. I am telling you that the data is consistent with this hypothesis in a way that should make you uncomfortable. Because every time someone applies the Fourier transform to a new domain, from heat to sound to light to radio to MRI to gravitational waves to quantum fields, and it works, the hypothesis gets a little harder to dismiss. The cosmological evidence is particularly striking. The cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe, is analyzed by decomposing its temperature fluctuations into spherical harmonics. Spherical harmonics are the spherical equivalent of Fourier modes. The resulting power spectrum, which plots the amplitude of each harmonic mode against its angular frequency, contains acoustic peaks that encode the geometry of the universe, the density of dark matter, and the ratio of baryons to photons in the early cosmos. Those peaks are literally frozen sound waves from the first 380,000 years of cosmic history. Sound waves in the hot plasma of the early universe, analyzed by the same mathematical framework that Fourier developed for heat in metal bars. I want you to think about what that means concretely. The large-scale structure of the cosmos, the distribution of galaxies across billions of light years, the geometry that determines whether the universe is flat or curved, the ratio of ordinary matter to dark matter. All of this information is encoded in the Fourier spectrum of the oldest light in the universe. The European Space Agency's Planck satellite, launched in 2009, measured the CMB with enough precision to determine the age of the universe to within 50 million years, the proportion of dark energy to within 1%, and the spatial curvature of the universe to within 1 part in 1,000. Every one of those measurements came from analyzing the Fourier modes of a faint microwave glow that fills the sky. The structure of the cosmos speaks in frequencies, and we listen with Fourier's equation. String theory pushes the resonance even further. In string theory, what we perceive as different elementary particles are actually different vibrational modes of a single type of fundamental string. A graviton is one vibrational mode, a photon is another, an electron is another. The properties of each particle, its mass, its charge, its spin, are determined by the frequency and pattern of vibration. As Brian Greene has written, particle properties are the manifestation of one and the same physical feature, the resonant patterns of vibration of fundamental loops of string. This is, at a very deep level, a Fourier decomposition of reality. The universe is a superposition of vibrational modes, and the man who first showed that arbitrary shapes can be built from pure vibrations was a tailor's orphan in revolutionary France. The Pythagorean echo here is impossible to ignore. 2,500 years ago, Pythagoras and his followers declared that all is number, that the universe is fundamentally mathematical, and that harmony, the mathematical relationships between vibrating strings, is the key to understanding nature. They were mocked for millennia as mystics, and then Fourier's equation, followed by quantum mechanics, followed by quantum field theory, followed by string theory, appears to suggest that they were closer to the truth than anyone in the intervening centuries. But I need to be honest about something, because intellectual honesty is more important than a clean narrative. There is a crack in this picture, and the crack might be worse than the picture. Everything I have told you about Fourier's equation, every application, every domain, every claim about the fundamental vibrational structure of reality depends on one assumption: linearity. The equations must be linear. The system must obey superposition, meaning if input A produces output X and input B produces output Y, then input A plus B must produce output X plus Y. When that condition holds, Fourier analysis works perfectly. You can decompose any solution into sinusoidal components, study each component independently, and add them back together. The components do not interact. They do not influence each other. They pass through one another like ghosts. Maxwell's equations are linear. The Schrödinger equation is linear. The wave equation is linear. The heat equation, the very equation Fourier was trying to solve, is linear. And this is not a coincidence. Fourier analysis works on all of these because it was designed for linear equations. Sine waves are eigenfunctions of linear operators. That is the mathematical reason the decomposition works. Feed a sine wave into a linear system, and you get a sine wave out. Only the amplitude and phase change. The frequency stays the same. No other family of functions has this property for linear systems, which is why sine waves are special, why they appear to be fundamental, and why Fourier's decomposition is so unreasonably effective across all of physics. But here is where the crack opens. Not everything in the universe is linear, and where linearity breaks down, Fourier's equation stops working. Not gradually, fundamentally, the decomposition into independent modes collapses because the modes start talking to each other. Energy moves between frequencies. New frequencies appear that were not in the original signal. The beautiful, clean picture of independent vibrational modes dissolves into something far more complex and far less intelligible. Turbulence is the most famous example. You have watched turbulence. Every time you have seen smoke rising from a candle, or watched a river break around a rock, or looked out the window of an airplane at the churning wake behind an engine, you have watched non-linearity destroy the Fourier picture. The Navier-Stokes equations that govern fluid dynamics contain a nonlinear term, the convective term, where velocity multiplies its own derivative. This means Fourier modes couple energy cascades from large-scale structures to small-scale structures through a process that is, as of right now, not fully understood by anyone. The Clay Mathematics Institute has offered $1 million for a proof of the existence and smoothness of Navier-Stokes solutions in 3 dimensions. That prize has been standing since the year 2000. It is one of the 7 Millennium Prize problems. It remains unclaimed. We cannot even prove that the equations that describe ordinary water flowing in a pipe have well-behaved solutions, let alone solve them in general. The physicist Richard Feynman called turbulence the most important unsolved problem of classical physics. Werner Heisenberg, on his deathbed, reportedly said that when he met God, he would ask him 2 questions: why relativity and why turbulence? And he added that he was fairly confident God would have an answer for the first question. That may be apocryphal, but the sentiment is real. Turbulence is the place where the clean, decomposable picture of physics breaks down into chaos. And it happens in the most ordinary circumstances imaginable. Every cup of coffee you stir, every gust of wind, every breath you exhale. Turbulence is everywhere. It is governed by nonlinear equations that defeat Fourier analysis, and we do not understand it. Think about what that means. Fourier's equation runs the digital infrastructure of human civilization. It describes quantum mechanics. It detects gravitational waves from colliding black holes, and it cannot handle water coming out of a faucet. General relativity is another domain where the Fourier picture fractures. Einstein's field equations are profoundly nonlinear. The geometry of spacetime depends on the distribution of energy, and the distribution of energy depends on the geometry of spacetime, in a self-referential loop that makes linear decomposition impossible. In general, the gravitational waves that LIGO detects are a special case, a weak field limit, where the distortion of spacetime is so small that the equations can be linearized and Fourier analysis applied. But in the strong field regime, near the singularity of a black hole, during the merger of two neutron stars, in the first fraction of a second after the Big Bang, the full, nonlinear equations take over, and Fourier analysis offers no help. The regions of the universe where gravity is strongest, where space-time is most dramatically curved, where the most extreme physics occurs, are precisely the regions where our most powerful mathematical tool fails. The early universe is perhaps the most consequential example. In the first instance after the Big Bang, during the epoch of cosmic inflation, when the universe expanded by a factor of at least 10 to the 26 in a fraction of a second, the physics was dominated by a scalar field in a regime that was not fully linear. The quantum fluctuations that seeded the large-scale structure of the universe, the fluctuations that eventually became galaxies and galaxy clusters and the cosmic web, originated in this nonlinear epoch. We analyze their consequences using Fourier methods, decomposing the cosmic microwave background into spherical harmonics. But the origin of those fluctuations lies in a regime where the Fourier picture may not fully apply. And there is an even deeper problem. At the Planck scale, at distances of approximately 10 to the negative 35 meters and times of approximately 10 to the negative 43 seconds, quantum mechanics and general relativity collide in ways that neither theory can handle. This is the regime of quantum gravity, the great unsolved problem of theoretical physics. At these scales, the very concept of a smooth space-time background on which waves can propagate may break down. The Fourier transform assumes a smooth, continuous background domain. If space-time itself is quantized, if at the smaller scales it is granular or foamy or something we do not yet have a word for, then the mathematical foundation on which Fourier analysis rests may not exist at the deepest level of reality. The equation that works on everything from sound to black holes may fail precisely at the boundary where the ultimate nature of reality reveals itself. I spent a long time sitting with this, and I want to share the discomfort it produced, because I think the discomfort is the point. We understand the universe works linear quantum mechanics, linear electrodynamics, the weak field limit of gravity, the laminar flow regime of fluids. These are the domains where physics is most successful, where our predictions are most precise, where our technology is most powerful. And these are also, by definition, the domains where reality decomposes into independent sinusoidal modes. The domains where Fourier analysis fails, strong gravity, turbulence, the earliest moments of the cosmos, are precisely the domains where our understanding is weakest, where our equations become intractable. where our predictions become approximate or fail entirely. This raises a question that I do not think has been sufficiently appreciated. Is Fourier analysis effective because the universe is fundamentally made of sine waves? Or is Fourier analysis effective because we have built our entire scientific framework around the parts of reality that happen to be decomposable? Are sine waves fundamental to nature, or fundamental only to the subset of nature that we know how to study? This is not a rhetorical question. It is a genuine, open problem in the philosophy of physics, and it cuts both ways. If sine waves are truly fundamental, then non-linear phenomena like turbulence and strong gravity are complications that arise from the interaction of fundamentally sinusoidal components, and we simply have not yet found the right way to handle those interactions. But if sine waves are an artifact of our mathematical toolkit, a lens that works beautifully on certain phenomena and distorts everything else, then our entire picture of reality, from quantum mechanics to cosmology, might be a view through a very specific filter, and we would not know what we are missing because the filter is all we have. I want to come back to Fourier now, because there is a symmetry in his story that I think carries weight. Fourier spent his final years in Paris, where friends and the mathematician Alexander von Humboldt helped him secure positions after the political upheaval of Napoleon's fall left him destitute. In 1822, the same year his masterwork was finally published, Fourier was elected perpetual secretary of the Académie des Sciences, a prestigious administrative role that gave him stability and influence for the first time in decades. He was also elected to the Royal Society of London in 1823 and the Académie Française in 1826. In his later years, Fourier became generous with younger mathematicians in a way that the establishment had never been with him. Dirichlet, who would prove the first rigorous convergence theorem for Fourier's series, benefited from Fourier's personal mentorship. Fourier supported Niels Henrik Abel, the young Norwegian mathematician who would revolutionize algebra. He championed innovative work whenever he encountered it, perhaps because he knew what it felt like to be dismissed. He also made contributions beyond his famous equation that are frequently overlooked. He pioneered dimensional analysis, the principle that physical equations must balance dimensionally, that you cannot add meters to seconds, that the units on both sides of an equation must match. This seems obvious now, but it was not formalized before Fourier. He was the first to insist systematically that physical equations are not just relationships between numbers, but relationships between quantities with dimensions, and that an equation which violates dimensional consistency is not just wrong, but meaningless. This principle is now so deeply embedded in physics that students absorb it unconsciously. Fourier is the reason they do. And in the 1820s, he made a contribution to climate science that is only now receiving the attention it deserves. Fourier calculated that the Earth should be colder than observations indicated if it were warmed only by incoming solar radiation. He proposed that the atmosphere must act as an insulating layer, trapping heat that would otherwise radiate into space. He compared the atmosphere to a glass box, an analogy that prefigures the modern greenhouse metaphor. He did not use the term greenhouse effect, and his proposed mechanism was not precisely correct. But he was the first person in history to recognize that something in the atmosphere was warming the Earth beyond what sunlight alone could explain. The man obsessed with heat, the man who could not get warm no matter how many blankets he wrapped himself in, was also the first person to notice that the planet itself was running a temperature. And then there is the detail about Évariste Galois. In 1829 or 1830, the young mathematician Galois, who was 20 years old and burning with frustration at the mathematical establishment, submitted a paper to the Académie des Sciences. Fourier was the secretary. The paper was lost. Whether Fourier misplaced it, whether it was lost in administrative shuffling, whether it was deliberately suppressed, nobody knows. What we know is that Galois never forgave the Académie. He wrote bitterly about the incompetence of established mathematicians. He died in a duel in 1832 at the age of 20, and the mathematics in that lost paper, the foundations of group theory and Galois theory, turned out to be among the most important work of the 19th century. Fourier, who had himself been a victim of institutional suppression, may have inadvertently suppressed the work of a genius even more radical than himself. The pattern repeats. His obsession with heat grew more extreme as he aged. He kept his rooms suffocating. He wrapped himself in blankets and heavy coats. Even in summer, visitors described the experience of entering his apartment as oppressive. His physician warned him. His friends worried. He did not listen. On May 4th, 1830, he fell while descending a staircase, aggravating what appears to have been a chronic cardiac condition. He initially refused treatment. On May 16th, 1830, he finally called for a doctor. It was too late. He died that day. He was 62 years old. The irony has been noted by every biographer who has written about Fourier, but I do not think any of them have stated it as bluntly as it deserves. The mathematician who solved the equations of heat conduction, who understood how thermal energy propagates through solid objects better than any person who had ever lived, may have hastened his own death by surrounding himself with excessive heat. The equation he wrote describes how warmth flows and dissipates. He could not apply that understanding to himself. He is buried in Père-Lachaise Cemetery in Paris. His tomb is decorated with an Egyptian motif honoring his years with Napoleon. Victor Hugo wrote in Les Miserables that in the Academy of Sciences there was a famous Fourier whom posterity has forgotten, and in some unknown garret, an obscure Fourier whom the future will remember. He was comparing Joseph Fourier unfavorably with Charles Fourier, the utopian socialist. Hugo was spectacularly, almost comically wrong. Joseph Fourier's name is inscribed on the Eiffel Tower, attached to a university, given to a lunar crater, and carried by the most important mathematical transform in the history of science. Charles Fourier, the man Hugo predicted the future would remember, is a footnote. There is one more detail, and it is the kind of detail that feels too pointed to be accidental. In 1849, the city of Auxerre erected a bronze statue of Fourier, their most famous son. It stood for nearly a century. During World War II, the Nazi occupation forces, who had been melting down bronze monuments across France for armaments, ordered the statue destroyed. On the night before the destruction was scheduled, the mayor of Auxerre secretly removed 2 bas reliefs from the base and hid them. The statue itself was melted down and turned into bullets or shell casings. The mathematical work survived. The metal tribute did not. Even in death, institutions tried to erase what Fourier had built. And now, I want to follow the implication to its end, because everything I have told you leads to a single conclusion that I do not think has been adequately reckoned with. Not by physics, not by philosophy, not by the educational system, not by anyone. The Fourier transform was written for heat conduction in 1807. It was suppressed for 15 years. It was computationally impractical for 150 years after that. It was reinvented for nuclear espionage. And then it turned out to be the mathematical operation that underlies the compression of all digital audio, the storage of all digital images, the transmission of all wireless communications, the construction of all medical images, the detection of gravitational waves, the imaging of black holes, the discovery of exoplanets, and the fundamental structure of quantum mechanics itself. Position and momentum are Fourier pairs. The uncertainty principle is a Fourier theorem. Particles are excitations of Fourier modes of quantum fields. The cosmic microwave background is analyzed in Fourier space. The large-scale structure of the universe is described by a power spectrum. String theory proposes that the fundamental constituents of reality are vibrating strings whose different modes of vibration produce different particles. Every layer of physical reality, from the subatomic to the cosmological, appears to be structured in terms of Fourier modes. And this was discovered by a man who was not a mathematician, who was not trying to understand the structure of reality, who was trying to understand why one end of a metal bar gets warm before the other, and who was told by the greatest minds of his era that his central claim was wrong. If this were just a story about a clever equation that turned out to be useful, it would be a good story. But it is not that story. It is a story about what kind of universe we live in, because the equation does not just describe the universe. In quantum field theory, the equation is the universe. The decomposition into Fourier modes is not a mathematical convenience applied to particles. It is the procedure that creates particles. Before the decomposition, there are fields. After the decomposition, there are photons and electrons and quarks. The particles do not exist independently of the Fourier analysis. They are the Fourier analysis, and that means you are the Fourier analysis. Every electron, in every atom, in every molecule, in every cell in your body, is a Fourier mode of a quantum field. You are not an object that can be described by an equation. You are a pattern of frequencies, a superposition of vibrational modes, a chord, if you want to think of it that way, played on fields that stretch across the entire universe. I do not know if that makes the universe more comprehensible or less. I do not know if the fact that one equation governs everything from heat to black holes means that we have found something deep about the structure of reality, or that we have found only the parts of reality that conform to our one best tool. I do not know if sine waves are the alphabet in which the universe is written, or the alphabet in which humans are capable of reading, with the rest of the text forever invisible. What I do know is this: a boy in Auxerre, orphaned at 9, collected the discarded ends of candles and melted them together so he could study mathematics in an empty schoolroom after the other children had gone to sleep. He was denied entry to the profession he wanted because he was not born to the right family. He was nearly killed twice by a revolution he believed in. He was dismissed by the most powerful mathematicians alive. He waited 15 years for permission to publish his work. And what he found in a dark room by the light of recycled wax turned out to be the syntax in which physical reality constructs itself. He never knew. He died in 1830 thinking he had solved a problem about heat. He had no idea that his equation would compress music, transmit phone calls, look inside the human body, detect ripples in the fabric of space-time, or describe the fundamental nature of matter itself. He had no idea that the attempt to prove him right or wrong would generate set theory, the foundation of modern mathematics. He had no idea that his equation, applied to quantum fields, would reveal that the particles making up everything in existence are vibrational modes, frequencies, patterns of oscillation in fields that fill all of space. He died in a room that was too hot, wrapped in too many blankets, having spent his life trying to understand the one thing, the one physical phenomenon that his equation was actually designed for. And the equation outlived him. It outlived Lagrange's objection. It outlived the Institute's suppression. It outlived the Nazis who melted his statue. It outlived every institution that tried to contain it. And it is still running, right now, in the phone in your hand, in the Wi-Fi signal passing through your walls, in the cellular tower nearest your home, in every MRI machine, in every hospital on this planet, in the LIGO detectors, listening for the next gravitational wave, in the radio telescopes pointed at distant stars, in the quantum fields that make up your body. You are a superposition of frequencies. You always have been. And the man who first proved that any shape can be built from pure vibrations, that even the sharpest corner can be constructed from the smoothest possible curves, was an orphan who studied by candlelight and was told by the world that he was wrong. He was not wrong, and what his equation says about what you are has never been fully absorbed, not by the scientific establishment, not by the educational system, not by philosophy, not by anyone. It has been sitting there in plain sight since 1807, running everything, describing everything, being everything, and nobody talks about it.